Can a visible object physically teleport straight through a solid wall? Well, I am Ruturaj Kulkarni and this is episode 11 of the Nobel Minute. With that, let's spin the wheel. Wow, we haven't had any Nobel Prize yet from the last 50 years and now we directly have last year's Nobel 2025. The Physics Nobel Prize that year was awarded to John Clarke, Michel Devoret and John Martinis. In the quantum world, individual subatomic particles can do something called tunneling, which means they can literally pass through solid energy barriers like ghosts. But for over a century, scientists assumed this ghost-like behavior was strictly limited to the microscopic world. They believe that once you bundle billions of particles together to make a visible object, they crash into each other randomly. This chaotic atomic traffic jam destroys the quantum effects, forcing the object to obey normal classical physics. So, how did this trio break that rule and force a large object to tunnel? They engineered a tiny 1 cm circuit loop made of a superconductor and deliberately blocked the electrical path with an insulating barrier just a few atoms thick. Normally, electricity hits and an insulator stops dead. But because they used a superconductor, something incredible happened. When cooled down, all the billions of free-moving electrons inside the circuit stopped crashing into each other. Instead, they synced up perfectly into pairs. And here is why it worked. Because those billions of particles synced up flawlessly, they stopped acting like individual classical objects. Instead, they merged to form a single massive collective quantum wave. When a quantum wave hits a barrier that thin, its probability of existing on the other side doesn't drop to zero. Without any added energy from the outside world, the entire giant wave successfully phased right through the insulation all at once, causing electricity to appear on the other side out of nowhere. They had officially proven that quantum mechanics can control objects large enough to hold in your hand. And here's today's fun fact. To keep that massive delicate quantum wave from collapsing, the team had to freeze the circuit to a fraction of a degree above absolute zero. That means inside their lab, this tiny microchip was thousands of times colder than the literal vacuum of deep space, making it one of the absolute coldest physical objects in the universe. But why does this matter? Because by proving you can manipulate a giant quantum wave inside a physical circuit, they created the literal hardware foundation for modern superconducting qubits, the physical building blocks powering today's advanced quantum computers. Their 1980s experiment took quantum physics out of theory and turned it into the actual tech of the future. And with that, I'll see you all tomorrow for the next episode of the Nobel Minute.